But
Scary.
if we're going fast enough, you catch some air. There's some issues. Some people won't catch air, and part of the reason is maybe their mass is spread out over such a long distance, right? That like ours sled's gonna be pretty long. That this, if you imagine, it's a little longer than this. Wow, it's almost twice that. And by the time the front starts to land, right, the back hasn't even left the ground yet.
Yeah.
So it may be that we don't see some catching air, and that's okay. But we'll have to just accept that, things will go different than we want. And truthfully, I think some of our sleds are going to break if they actually catch 10 feet of air and then impact the ground. It may like shatter, and we don't know. We don't want that either. Yeah. But you may feel in your lawn chair strapped to the sled that your butt is up in the air for a little bit, and you feel this bunk. Although watching from the side here, we would see that the back of the skis never left the ground. You'd still feel like you're catching a little air. I don't know, we have to maybe decide if we're going to count that. How do we measure?
Maybe it's just your body.
Yeah, maybe just try and estimate the center of mass and see where it... Yeah. So we'll have to see. But so we're gonna launch ourselves horizontally. It's going to make the math easier. Okay, so first of all, there are some formulas, and there are 3 formulas that are called the kinematic formulas, and we use them to do all sorts of stuff like send probes to Mars and land them on the surface, and figure out how to get things back from the moon and all. We can do lots of physical calculations with 300 or 400 years old math. Okay, so this one is velocity. Let me do this. They either solve for distance or velocity. So this distance equals your position plus your velocity times your time plus 1/2 AT squared. Now, do you remember using 1/2 AT squared?
Yeah.
Right, so that's how far something's fallen in free fall. If we can just measure the time and get that with a stopwatch, right? We can say whatever the time we got in the stopwatch was squared times 1/2 the acceleration of gravity, and that's how we did that stuff with Coyote, right? Okay. If we have then just like a simpler problem with no acceleration, but just velocity, like a car is driving at 60 miles an hour, we can just multiply velocity times time, right? So we could say, I'm going 60 miles an hour. How far have I gone after an hour? Well, my speed is 60 miles an hour. Every hour I go 60 miles. So after 1 hour, I've gone 60 miles, right? After 2 hours, I've gone another 60 miles. That's 120 miles, right? So my velocity times my time gives me a distance here. So I could say my distance is my original position, and you'll see this written as I for initial or O for original, either way. And I posted a link for you guys, a little video of this woman going through a similar math problem, and I think she says I for original. But so, plus now, I could have this jump a little different. I could have it more complicated and have it pointing at an angle. So there's a steeper slope, and the jump has already, as you leave the jump immediately, there's downward velocity, right? Ours has 0 downward velocity, which makes the math simpler. We're going to have all of our force turn horizontally and be shooting us out this way, and then we'll still drop, right? We're going to have some projectile curve, but it will be, only thing making us go down is gravity. All of our velocity from going down the hill is making us go this way, and gravity can't do that, right? So we'll start with 0 drop happening, and then as we're in the air, no ground supporting us, there's no normal force pushing up, we'll start this free fall thing. So now we'll have 2 components. We'll have a vector going horizontal, which is just velocity, has no acceleration. And then we'll have this vector going vertical, the y direction, and that's just the acceleration of gravity, right? But you could have a ski jump with both components. So here we have 8 basic formulas. There's only 3 of these kinematic formulas. We're going to use this one today. Okay, so first of all, I want to talk about this y component. Okay? So I'm going to say here my, how do I do this? My final position in the y component is going to equal, I'm going to use this formula here, my y initial, my initial position, plus my velocity. Now I'm only talking about the y component right now. Later over here I'm going to talk about the x component. So I'm breaking this down to my two component variables, and I'm only talking about y. What kind of velocity am I starting with in terms of the downward force or downward direction? No, yeah, 0. It's all going out horizontally. So my velocity in the y direction here is 0. So 0 times anything is 0. I can just cross that off. We don't need that part of the equation for this because I made the jump horizontal here. So I'm going to have my initial position plus this component here. This, by the way, is from Newton. This is from Galileo. So here we have my 1/2 at squared. I can simplify that. What's 1/2 acceleration of gravity?
5.
Yeah, so right away I can get rid of one variable. I'm going to say 5 meters per second squared times time squared. All right, so there's my formula. And I'm going to say that this position, wherever it is we land on the ground, we're going to say that's 0. Right? And then the height is whatever this distance is, y above that. That's going to be our initial position, will be our height. So we're going to say this is the ground, and the initial position is the height above it. So I can now say that this is 0 equals, I've gotten rid of one variable now, right? And I made our math pretty easy by setting it to 0. So I'm just going to have the only y in here will be this. I want the magnitude of this side of a triangle now, right? And I don't need to worry about y initial or y final. So I just want y. And plus, now this is interesting. I got to say negative 5 meters per second squared times time squared. Yeah. Why is this negative?
Because you're going closer. The distance is decreasing.
The convention is, and move any direction, any motion away from the Earth is positive, anything towards the Earth is negative. So because this is falling back down, we're calling this negative. All right, now I can solve this for y and say y, negative y, equals negative 5 meters per second squared times t squared, right? And these will cancel out. So I got y equals this. That's pretty simple, okay, for the y component. Now what I really want to do is, we're going to go out there that day with a shovel. We're going to make our snow slope. And we're going to have a level. We're going to bring this, we're going to measure the angle. Make sense? So we're going to say, oh, it's 30 degrees. We're just going to literally dig our jump. We're going to put a level on and make sure it's horizontal here, it's flat. And then we're going to put this thing over here, and we're just going to measure. We'll just eyeball it. They used Google Earth in the past, which was really inaccurate. They just looked at the maps and calculated the slope. They took two positions and, tried to estimate it. So we're going to actually just measure it by eyeball, and if we're off by a degree or two, we just don't care. All right, so we're also going to have Officer Conologue measure the velocity, so we'll know this number, right? And apparently we're going to need to know our hang time. We'll have a stopwatch here so that we can know how long we're in the air. That's kind of a pain. Okay. We're going to get rid of this later. My point is we want to reduce these variables as much as possible. So what I'm actually going to do is I kind of solve this right now using old school Newton and Galileo, right? Let's see if we can solve for y using trig. We're going to see what that would look like. So I want to, we'll forget about x. We're talking about the y component. And I do care about this, right? That's the whole question I'm asking you guys. Is what's the distance, right? This, I'm not going to ask you to solve for x or y. Imagine this is the ski slope and the jump is horizontal, like this height. And you land over here. I could say, I want you to calculate the distance of the x and the y components as well. But to me, that's ridiculous. Like, who's going to ever be skiing and say, like, okay, so they landed here, so vertically, that's about this, right here would be, but what is that distance, the x component of this motion? Like, I just want to know, where'd you land on the slope, right? So I'm really interested in D here, right? But so we're going to set up some trig. For now, we're going to continue. I'm interested in the y component. So which of these formulas do I need here to get the side opposite my angle and the hypotenuse?
I have questions.
Yeah.
So are we getting the distance from the top of the jump to the ground?
Yeah.
So from there.
Top of jump to there.
Okay, so the X is not the. I thought the X and the Y were actually like the jump, but that's not the.
No, sorry.
This
is.
Okay, that's not the jump. That's just distance. And,
yeah.
Okay.
Here's the ski slope. Here's our snow slope right here.
And
here's our jump.
That's your jump.
And then this is the distance on the ground I'm
Okay.
really interested in. That's
Okay.
Okay, does that help you guys? So I just, broke this down into two vectors. I took this motion, this distance, this movement, and broke it into how far did we go horizontally? How far did we go vertically?
Yeah.
Thank you, Daggers. But now because we can talk about it in that way, we can look at this angle, which we measure, and we can also solve this with trig. So I got the sine of 30 degrees would be the opposite over the hypotenuse, right there, right? I could say that I'm keeping the y direction in purple. We could say that the sine of 30 degrees equals whatever the magnitude of y is over the distance. This is really in black. That's the thing we're trying to find always, is the distance. Now, I'm going to solve this for d. I could just multiply both sides of this equation by d. Right?
Yep.
By d over 1. And then these would cancel out. And now I've said d times the sine of 30 degrees equals y. Does that make sense? Okay, so I've got this equals y and this equals y. And now I can say, well, they equal each other and start canceling out some variables. So what I'm going to say is 5 meters per second squared times t squared equals d, that's the thing we really want to find ultimately, d sine of 30 degrees. You see how I got that?
Yeah.
I solved for y using old school, that's Galileo. I solved for y using some trig, but they both equal y, so I said they equal each other. Now I'm going to come back to this, okay? This is going to be really important to us, but I'm going to come back to it. This is cool, if you want to geek out, because I use Galileo and some modern trig, and I said they equal each other. My whole point is I want to simplify this and get rid of, I've still got two variables, and I want to try and get rid of this t. Okay, so I'm going to come over here now, and I'm going to solve for x. I'm going to write that stuff in green. So here I got my y. Here I'm going to write some x stuff over here. So I could say x equals, well, this, velocity times time, right? I got my velocity right here, and I just got my time with a stopwatch. So my velocity, I'll write it in orange so you can tell where I got that number from. That equals, 30 meters per second. Where'd that number come from, by the way?
Analog.
Yeah, I made it up, but we're going to measure it when we go out there. We're going to have a radar gun, and we're just get that number. So you don't have to calculate that. We're going to tell you what that is. Okay, so now I'm just going to use that velocity. I guess we're going to have a stopwatch and get the time. So this times time tells me my distance, right? Okay, let's do the same trick here. Let's also solve for x with trig and see if we can cancel some stuff out. So I want to solve for x here. I want to use some of this SOHCAHTOA stuff. I want to use this d component, because truthfully, that's really all I care about, is how far down the slope did you go, what's this distance. Okay. So I'm going to say x over d. This is adjacent over hypotenuse, that one.
Cosine.
Cosine. So now instead of using sine, I'm going to use the cosine. I'm going to say that x equals, say the cosine
30.
of 30 degrees equals x over d, right? Now I could then multiply both sides by d, and now these will cancel out, right? So I have x equals d times the cosine of 30 degrees, and I also have x equals 13 meters per second times t. All right, so I'm going to set them equal to each other. I'm going to say 13 meters per second t equals, I want to do this always in black. This is the thing I really want to find, d cosine 30 degrees. All right, so how can I solve, what would this look like if I solve for t? I want t alone on one side of the equation. How could I do that?
D cosine 30 divided by 13 meters per second.
Okay, I can just divide by 13, right?
Yeah.
So I could say then t equals,
Was your head getting hot?
my bald head's not used to having, hair. Cosine 30 degrees over 13. That's meters per second. Right? Okay, now I solve for t. Do you see why that's awesome?
Because you have T already.
Yeah, now I have t. I didn't even have to measure it with a stopwatch. I can just say, we're going to go out there and all we're going to get is, we're going to use this thing and get the angle. We're going to use the radar gun and get a speed. And now I can take this component here, this whole thing, and just substitute right there for t. So I'm going to do that now. Now I'm going to write, now the only variable left would be d. I'm just going to write in black here. That's what I really want. I'm going to say 5. I guess that has to, meters per second squared. And then parentheses,
Square
this
that.
whole thing, right?
Yeah.
T equals d cosine 30 over 13 meters per second. And this whole thing has to be squared. That's probably going to be the thing people mess up the most.
Yeah.
For remembering that there. But so now this whole thing is squared. I'm going to write it differently because we're going to plug this into our calculator. I'm going to say this has to be squared, and this has to be squared, and this has to be squared. And now I don't need to write it outside the parentheses. Okay? Now that equals d sine 30 degrees. This d can cancel with one of those d's. And we have something that we can just solve, right? Where's my phone? Can someone pull up a, oh, you resent it, thanks. Can someone pull up a calculator?
Yeah,
So, this, by the way, we have 1d over here. We're just going to plug in some numbers to get an answer. But what I did is I left d on this side of the equation, and I divided by 5 over here. And I multiplied by 13 over here, and I divided by the cosine of 30, and then I just, that's the formula you got. I suppose I might as well write it that way now. So this ends with the formula that you have on that other paper. So I'm going to say then, I'm going to reorganize this so that the only d left is here. To get it alone, I'm going to leave it where it is, but I'm going to divide by this, multiply by that, divide by this, and have everything else on the other side, right? So, it's okay if I erase this, d? Erase that. Erase this. I'm going to say, I want to get this over here, so I'm going to divide by 5 meters per second squared. I'm going to divide by the cosine of 30. Oh, I got small. Cosine of 30 degrees. Damn. Squared. Right? So now I've got this canceled out. I've got this canceled out. I'm going to multiply this by 13 meters per second. And this 13 has to be squared. So I'm going to put a 2 up here. Okay, so calculator, sir, would you do me a favor? Would you take 30 degrees and do the cosine and square it? And do you have to like do memory plus, put that, store it in memory? Okay, so we're going to come back to this component. You already got that. Will you take 30 degrees and take the sine of it?
Check that.
Ooh, someone else with a calculator, quick.
Sine of 30 is half.
What'd you say?
The sine of 30 is half.
Yeah.
It's
0.5.
0.5?
0.5.
Okay.
Yeah.
I think, I know from doing this last night, that this is actually 169, 13 times 13.
That's
Good?
true.
Okay, so would you take 0.5
Okay.
times 169?
84.5.
Yeah.
84.5. Would you divide it by 5?
16.9.
Would you divide that answer by whatever you got in memory? Memory recall.
Right.
This component here.
22.5.
22.5, and this is in meters. Real quick, I want to do this. We got
That's a big jump.
it's a big jump.
Jeez,
Yeah, that's a
Louise.
big jump. Now this turns
That's
out
a
to
jump
be
and a half.
this turns out to be like 30 miles an hour.
Yeah,
Okay.
you're going. Yeah, the calculations are pretty big.
Yeah, and then I think also our angle,
Yeah.
I bet on the ski slope would be that maximum. I think you get to 40 degrees and you feel like you need an ice axe. This is really steep to walk up. I'm betting we'll be doing something like 20 degrees. We'll see.
Yeah.
All right. Anyway, oh my gosh, that's a lot of stuff, right? However, since I canceled these and put them over there, this side of the equation now reads like this.
You just rewrite that. Just
D.
add that one.
And now, I'm gonna do this. There's our answer. But this, this is the formula. I want you to understand it. I want you to explain how to use it. But all you need to do in your calculations is, I've explained it to you. I've got another video that goes through a similar problem and will explain it to you, and that's already posted. You can stop filming, and thank you.